This normalization thing is a very nice example of how we use one of these computational models to try to understand what the brain is doing, but also what behavior is doing. And so this is one of the final sort of concepts in the lecture series that I try to really explain, right? And then in the podcast and in the papers, you get a bit of a broader view on what's going on in terms of the field. But I think this is a really nice example of how you can capture very complex behaviors and signals using a very simple model, right? A very parsimonious model that really is very broad in the types of things that it captures. And that's why we ask ourselves, like, is this what we could call a canonical computation? So a canonical computation, like the cannon, right, is not a cannon that you shoot projectiles with. The canon is the agreed upon sort of center part of a corpus, right? Like the canonical parts of the Torah, right? That sort of thing. That's what we mean by canonical. So very, very central computation that keeps recurring. So in the lecture today, I'll give you I hope an idea of how that would work. Right? If you try to use one single concept, one single sort of computational model to capture many different things, and how does that work, and where does that come from? But I try to start with a bit of history, because well, that's always a nice way to start. The point being that people have been interested in this sort of phenomenon for a long time. They have, like researchers have always been thinking like, there has to be some sort of general principle behind how the brain works. And if we find the key to that general principle, that's when we really learn so much more about the brain, right? That's like a multiplier. We understand the single mechanism. If the brain uses it 20 times, then we understand 20 different brain functions all in one go. So people have been really searching for that type of principle for ages already. And so one of the things that I'll be talking about today is this normalization principle, where these two like researchers posit that this divisive normalization thing that we'll be talking about today is one of those canonical computations that the brain reuses over and over. And this is something that that keeps recurring in the literature. There's many different papers that sort of talk about this normalization principle as a canonical computation, as an atom, if you will, of neural computation. And this spans different principles, right? So you can look at neural recordings, like direct neural recordings. You can look at fMRI recordings. You can look at behavior, perception, value-based learning. All of these you can sort of apply this phenomenon to, and that's why people think that it's a canonical thing. Right, so this is really one of those things that researchers want, right? Because that will give us a general principle, a parsimonious explanation of how the brain works. Because usually, and this is what the course also started out with, right? The brain is like one of these biological systems that's really, really messy, right? And neuroscience is very data rich and theory free, theory light. So that really makes it a sort of holy grail, right? If you can find one of those overarching principles, then yoo-hoo, right? So when people started looking at like how can we find these canonical principles of brain function, what they did is they started out just by looking at the anatomy of the brain. And if you do that, you see, and this is something that Marr, from the 3 levels of description, Marr also noticed, right? You look at the neocortex, which is the largest part of our brain, that, the folded stuff on the outside. And you see that, and I'm going to point it out with my, here we are. So you see that this dark stuff is in this staining the neocortex, the gray matter. It's where the cell bodies of the neocortex are. And you see already, like at the A here, around the A, you see that there are like different layers. It goes from dark to white, or to light to dark to dark to light to dark, right? It has these layers in it. And this seems to be recurring, right? You see this layer structure here also. It's quite similar. And you see it here too, right? It seems to be more or less everywhere. It's very beautiful here, by the way. See? there's like this structure that keeps recurring. And so Mar already wondered, like, is this uniformity of anatomical structure, is that a sign of this being used for information processing in a similar way? So very much focused on this, anatomical thing that you can see here. What you see here on the right is an atlas of cytoarchitectonics called the Brodmann Atlas, which really shows how these layers structure. This layer structure is repeated all over the cortex, but certain layers are thicker and the cell types differ a bit, and that's what's shown in this cytoarchitectonic atlas, is what people call it. So there's a lot of there's signs of how a certain computation might be performed by a certain circuit, and if you see the circuit recurring, then you might think, could this have a functional role? And so the first thing that people wanted to focus on is really this circuit level explanation. And so what you see here on the left is that layer structure of the neocortex. People usually designate 6 layers, and certain specific roles are sort of tied to these different layers. For example, the layer 4 here in the middle, that's usually thought to be an input layer. So input comes in from lower levels and then hits that middle layer, and then the information goes up and down, where it gets transmitted to higher level processing. So people really thought, like, how do we have this circuit? And we know what that's about. Yeah? So we have a biological circuit. Here you see a couple of examples of how people might lay out a circuit. Yeah. And say, like, for sort of electrical engineering standpoint, right? If we have the connections between the different cells, we can sort of draw it out as a diagram. For example, here you have, I think this is like a basal ganglia type model where you have the afferents 1, 2, 3. So AFF stands for afferent, which brings in information. And then you have efferents that bring out the information. So that's EFF. And so you can draw these diagrams of what the neural circuit is like, from a very sort of engineering type approach. And here's another couple of examples how people have sort of focused on doing that. And so people did that for a while. Sorry for the slide thing. And so people focused on this canonical circuit property, right? If I can make like a PCB, like a print board, like with connections on it, is that the level that I can describe this with? And it turns out that that's not really the way to do it, right? There's many different specific phenomena that map onto these circuits, and I think the point here really is in red, and I'll go into that in a bit also. You can have one of these circuit level descriptions, but it's really, really dissociated from function. Yeah, it's just an engineering diagram. And so in the 70s and 80s, people were really involved in like drawing out these diagrams, but you need to have what this thing is doing. You need to have that also, right? And this is what's called this computational account here. Only then can you give meaning to what the microcircuit does. Yeah, so the microcircuit, how the neurons are connected, is actually not really what we should be talking about, right? We shouldn't be talking about this canonical circuit, for example, of the layers of the cortex. We should take this to a different Marian level, if you will, and talk about the computations that the brain is doing in a canonical way. Yeah. So it's kind of ironic that Mar said we need to focus on circuits, right? And then we have to like years after he's dead, we have to think like, but maybe we shouldn't be talking about circuits. We should take it up one Marian level, right? We have to talk about these computations in a slightly more abstract way, and not talk about the circuits, the implementation, if you will, level. Yeah. And only then can we start to relate what the neurons are doing to what cognition, for example, is doing, right? We want to draw that link between the brain and the mind. We need to be there in between, right? We need to have a computational account of what's going on there. Is that clear? That distinction between the circuit and the computation? Good. So then if you want to search for canonical things, right, you step away from trying to find canonical circuits, and you start to wonder, what are canonical computations? And so what are the sort of generic computations that the brain performs? And it's a different outlook, right? You're not looking at connections between neurons. You're really taking a step back and looking at it at an abstract level, at a more abstract level, right? But this is, of course, something that people, it's sort of democratic process in a community of scientists. Like, is this canonical? Well, that's a fiat level thing, right? If enough scholars think that something should be in the canon of the Bible, that's when it ends up in the Bible, right? And the same happens for deciding whether something is a canonical computation. Like, what I'm doing today is showing you the argument, right? Why this would be a canonical computation. Yeah. Because like the cortex does many things, right? And so we shouldn't be fixing ourselves to a single canonical circuit, but a broad array of reusable computational primitives, right? So that's really also the idea of a canonical computation, that it's this principle that you can apply in many different contexts, right? So that the many different computational sort of demands on the brain can be met with a single principle. Great. And you already see the answer there, right? A candidate computational primitive would be normalizing, and I'll talk about that in detail, but the ratio between the activity of an individual neuron and a set of neurons. And I'll go into detail about that, because that's really going to be like the core of the lecture today. Yeah. Right, so we're going to this idea of this abstracted idea of how can we look at things as computations instead of circuits, because circuits, and this is something that I don't think it's in the list that you could choose it, but I highly recommend this this podcast number 130. It talks about the research of this Eve Marder. It's I think she's a professor somewhere at Boston University or Tufts University, somewhere in Boston. And what she's shown in her research, which is like it's spanning like 50 years of research, what she does is she researches the stomatogastric circuit in the lobster. So she goes to the harbor every morning and gets lobsters fresh from the sea, and then analyzes like the neurons inside the gut of the lobsters. Why would that have anything to do with what we're interested in? Well, she has found that you can have different specific circuits that do between individuals. You have slightly different circuits, and they still do the same computation. But more importantly, what she's shown much more dominantly is that usually these are all the same. So the circuit is fixed. But the circuit can go into all sorts of modes of activation. It can perform many different functions. So what that means is that there is a sense of degeneracy there. You can have the circuit, but that doesn't say anything about the actual computation. So in this case, computation is in the gut of a lobster, right? What that means is that it will do like a normal gastric cycle type thing, or it will regurgitate, or depending on the temperature, things might have to change and things like that, right? So there's a lot of flexibility in what the circuit is doing in terms of the computation that it's performing. And in this case, computation is digestion. Still, what's important here is that it's the computation that matters, right? And not the circuit. So we want to look at this at an abstract level, and the hardwired circuit doesn't really tell us that much. So we're stuck with this sort of idea. We now need to search for canonical neural computations. And so what are they, right? Where do we find them? Well, we find them in the brain. It's not a big deal. Like, that's not a very hard question. But what we're searching for is, like these quotes say, like a really diverse set of computational building blocks, and then you can create this broad range of reusable computations, right? And so people talk about this as computational modules that you can reapply in different contexts to have the same fundamental operation perform a different role in each of these different contexts. Yeah. And so that's the paper that you'll be reading also, right? That you are reading perhaps already. That is a very broad paper, and I'm going to give a sort of slice through the paper and hope to make both the paper and the second practical a bit more digestible. Okay, so people have talked a lot about this, and actually you could say that we've already encountered one of these canonical principles of computation. So we've talked a lot about these receptive fields, right? And you could say like, okay, we have this, maybe even the perceptron is a part of this, right? Just this sort of input-output type thing. It's what we think a neuron, an abstract neuron, is doing. In this sense, it represents something by virtue of its weights in the outside world, and it can do so in a sensory space, in a semantic space. We've talked about that in terms of the receptive field analogy, right? We can talk, and it can be like a place cell also in real world space, in abstract spaces, right? So that's one way of thinking of a canonical computation, like one example where this motif, people have also refer to this as computational motifs, where that recurs. One other one that's really hip and happening is this idea of predictive processing. That is to say that we think of the brain, or many people think of the brain as this sort of hierarchy of loops, where all information flowing from the outside in is like a prediction error. And also everything flowing from the inside out, right, from the top of the hierarchy downward, is predictions, and they get compared at each of these levels. This is a very elegant way of thinking about the brain that hasn't received a lot of sort of empirical grounding as of yet, but it's a very people find it a very appealing way in which to think about how the brain works, right? And you can think like, oh, this should recur. We extend in time as agents, as brains, and so we need to do some type of prediction. Also, something that keeps recurring, and it's something that you see also in reinforcement learning. You see this concept. You see it in how people think about perception. So it's a very broadly applicable type of thinking. And so I'm not going to talk about that because it's not my pet theory. But this divisive normalization is. So we do have a lot of low-level evidence for this idea that this divisive normalization that I'll be explaining is like a core canonical computational principle of what the brain is doing. And so the rest of the lecture is me explaining that. Can you think of any other canonical computations?
I think they all have a lot in common. It's like inputs, weights, output, but yeah, Bayesian prediction error is more set of weights and more inputs and outputs. And divisive normalization I never heard, but it's like it's something like abstraction.
Exactly, yeah. And so what you see here is this an interesting way, like there's overlap between these, right? You need something of a receptive field to be able to do predictive processing, but in that case, the receptive field may not be, so like the weights may not be over just an input space, but also in terms of predictions, right? You could have that would just be the space in which the receptive field lives. You need receptive fields because, that's what the input may be in the divisive normalization way. There's other ways in which these different things could integrate, right? So this other inputs, it's a very broad term, right? Other inputs, what if that is a prediction, right? So you see that this is really almost philosophy, right? This is really like a high-level way in which you can try to think about what the brain is doing, and they can blend together. What's important is that, you know, it's all nice and good to think about these things at this higher level of, you know, canonical computation and principles, but it's important to then be able to dig down and really start to see, how does this model explain my data, right? Because, you know, fitting parameters and making the model fit the data and then interpreting things really has to be a part of this scientific enterprise, right? We can't just philosophize. It needs to connect to data. And so I hope to be able to show you how, at least in the case of this divisive normalization, we can do that. Yes. Yes. I'm going to talk about that a bit in a few slides. It's always the sign of a good question, right? I don't know if I said this, but the sign of a good question, yes. I always say that. A broken record, man. Yeah, so I'll go into that in a bit. Okay. So we've talked about these receptive fields, right? And they can exist in many different spaces, all nice and good. But that's all more or less just this left side of the diagram that I just showed you, right? This input-output sort of thing. But we know that there's a lot more going on in terms of what the brain does, right? And what I mean by that is there is a lot of influence that goes into the response of a single neuron based on what other stuff is doing, right? That's context. So it's neural context. It can be temporal context, spatial context, anything that you can make a receptive field for, essentially. And so just to give you an example, right? Just to show you how this contextual modulation, if you will, works. Which of these four elements on the left is at the center of the thing on the right in this gray thing? Those of you that get it right, you get €2. No, the ones of you that get it wrong get €2. The ones that get it right, is this also 2? Yes. The ones that get it right get paper money. So which is in the middle?
The first one.
So the second is from the top or from the bottom?
I would say the first from the top.
Yeah, so let's vote. I'll go down, right? The first. Yeah? The second? The third? The fourth? That's you three, right? You don't know?
They don't like to vote.
Oh yeah. You're what is that? So you see that it's really hard already, right? It matters like where you just put your eyes, and that sort of thing. Yeah, I'm not gonna be able to get rid of all my money, but you win. And all of you picked the first? Oh no, that was my only €500 bill. I'm sorry. I'll give you 2. And so so this is what you get when you celebrate. You don't even have to vote to get rich.
Thanks.
Huh?
I'll take them.
Right. Excellent. I don't know which is more chocolate. I don't even know. Yeah. Yeah, there's more for the next question at some point. Yeah. So what's the right answer? Well, you know from the rewards, it's the top one, right? But especially when you just present these things really quickly, people tend to vote for the lowest one or the second one from the bottom, right? And this is actually they vary in contrast. So the upper one is 40% contrast, where 100% would be full black and white as a range, and the bottom is 10%. So you can actually shift what people perceive as contrast, which is a really important thing to see, by something like 20%, and that's an insane amount. Because normally you'd be able to see differences in contrast. If I just show you the same pattern at 24% contrast or 25% contrast, you'd be pretty good at saying which is the higher contrast, right? So this is really a huge range of differences. And you can sample this sort of thing with what we call a psychometric curve, right? So where you show different contrasts, in this case in the center, and then you you tally probability of reporting the target is higher contrast, right? So you can give like next to some reference. And so the red one is when you do this without a surround, and you see that people are very close to veridical, which is the truth, right? This, I think the reference contrast in this case 20% or something. No, it can't be like 60% or something. And you see the green one is when you present that surround around it, and it just pushes that entire range away. It's a huge effect, right? So normally you'd be really good at it, and like 2% contrast differences you can already see, whereas it just the effect here is like 20%, like 10 times what you would normally be able to perceive as a difference, and that's what you report. So it's a huge effect. I can keep saying that, but I won't. Right. So what I mean to say by this is that context is hugely important in how we perceive things, right? And what that means is it should also play a very, very important role in how our brains pick things up. Yeah? You just saw it, right? This is what your brain just did. Your brain's fault. So this principle of divisive normalization, it's pretty old. It was developed in the 92 by David Heeger, who was also one of the authors on that review paper that you're reading. And the idea is really, really simple. You take this input that you normally would see as creating a response, right? There would be a direct link going from the input to the response. But in this case, you don't just say, it's, this is some multiplier to a response. No, you say, but there's also other inputs. And they may be neurons that are right next to this neuron. It may be signals coming from a completely different region. It could also be the past activation of the same neuron. This can be seen in a very, very general sense. Other inputs, and we divide so we sum the other inputs, they become one single thing, and then we divide the input by that, right? So we're looking not at just one response, but at a ratio of responses, which we already saw in this piece of text, right? Geez. So what in this case happens is that these other inputs, they represent the computational context, if you will. And what I hope to convince you of and hope to show you is that just this division serves as a sort of computational building block to create all sorts of contextual effects and optimize processing in a very, very straightforward way. So this principle was first proposed to explain nonlinear sort of suppression of responses or compression of responses. So so in the 90s, people became better at looking at single cells in V1 and what they were doing, and they found all of these weird things happening that didn't really fit the standard linear concept of a receptor field. Yeah. And this David Heeger thought of this way of doing that, and it turns out that by this principle of just saying like, there is a neighboring population of neurons, and we divide the activation by their activation. It turns out you can do a lot in terms of like contrast saturation, surround suppression, a bunch of these different nonlinear, more complicated types of processing we can see. And after this happened in 92, this principle was identified as something really, really promising, and people started applying it to many different types of processing. So if you look in the literature after 92, people started looking at olfaction, same principle. You can explain the neuronal measurements by the same principle. Same goes for retinal processing, same goes for multisensory integration. I'll show you an example of these population receptive fields that we can measure using fMRI, and I'll show you an example of how attention works. So even high-level cognition, and people have actually applied this to value-based decision-making also, like these anchoring effects. You can actually explain also by this very, very simple thing, this idea of we don't just have a response from an input, we also divide by the rest of the input, more or less. Yeah? So it's a very, very powerful phenomenon that David Heeger thought about. I'll post a YouTube video where he actually gives more or less this lecture, but much better than I can, somewhere in New York. It's a very nice presentation that he gives, so I'll link to that on YouTube. Yeah.
She's more like curiosity of topic, but we
Uh-oh.
always look at neurons like when you see images, maybe they're not the reality, but we see them connected to each other, but they are a bit like in a vacuum, like in a space. Like in reality, that doesn't exist. It's just more connections with other neurons, so there is actually space between the axons of the neurons.
Oh yeah, you know these beautiful simulations where you go between the neurons and you see them firing even, right? You see the action potentials go.
But my was because like since, for example, seeing a neuron here and another neuron here, they are connected.
Yeah.
What is not connected to them but very near them might be those other inputs, and that's why I was asking like what is around those connections? Is more connections? There's no space for nothing, or is that there's actually like space or some kind of water or some kind of glial cells around? Glial cells?
Yeah. So there's a lot of so neurons are like you know the engine of a Ferrari, right? It needs to be, you know, it needs fuel, it needs ventilation, it needs all of these things, right? And they are like neurons. They really use a lot of energy, a lot of oxygen also, and so you need this entire support structure around it, glia cells, but also vasculature. Like there's a lot of like biological scaffolding that's needed for the neurons to be able to function. So like, and there's it also varies a lot, right? So certain neurons have many more connections than other types of neurons. The way they receive inputs into their dendritic trees differs a lot. Right, the shape of the dendritic tree also changes a lot depending on the function of the neuron and what brain region it's in. Yeah, there's not that many sort of common denominators there. But if you see one of those beautiful animations of these neurons where the camera just tilts like between the neurons and you see the action potentials fire and you see like 10 neurons or something, no, it's all yeah, that's completely fake. And there's glial cells between them. You know, just the sheathing of an axon, right, where the action potential goes through, if that's myelinated, there's like these glial cells around it, Schwann cells, what they're called. So there's, yeah, it's much more complicated. You should look up an electron microscope image of neural tissue, and then you'll see it. Like it's completely packed, and 90% of it is not neurons.
If an fMRI, we are measuring the vascular.
Exactly. Yeah. Yeah.
Thanks.
Yeah, no, but it's a sort of a tradition and a sort of heritage that we don't really know how to work with in computational cognitive neuroscience or in neuroscience in general. Is really that people would like take these single electrodes and then hunt for a single neuron that they could find. Now, when do you find this neuron? When it's a big neuron. Like when it's a big neuron, the electrical fields that it produces are larger, so you'll be able to pick it up more easily, right? So so it's all sampling bias, right? That you get, you end up with a neuron. Well, you're only going to end up with bigger neurons. So people really didn't know. So these are the large pyramidal excitatory neurons in the cortex, but there's a lot of smaller inhibitory neurons that are there, and that people would never pick up. And so, yeah, there's this transition from this sort of bias sampling single neuron tradition to this, what we're doing nowadays is much more broad sort of sampling, where we can actually identify also these inhibitory neurons, for example, different function type neurons. But yeah, that was a big digression. Yeah. I think we should have a break because it's 14:14. It's just a beautiful time to have a break. Of course, yes, please.
The other beats, there are ups and downs. Yeah, I don't structure of the neuron stuff.
Yeah. So yeah, so the input to a response, just see that as a perceptron, right? So you have input can be like a pattern. You have a set of weights, and then you go to a response. So that the simplest way of seeing that is as a perceptron. Then the other inputs, they're not part of the whole perceptron thing, right? And so we have to, I'll talk more about what that is, but yeah, this is the most abstract way of looking at it, like input, other inputs, right? But we can make this much more concrete, and then we can actually start to try to explain data. Yeah, great. And so now we're going to get to your question. I mean, great. Yeah. Right. So normalization. Yeah, this division. You can think of how in a neural network you would implement this sort of thing, but it's not really implemented the way that it's implemented in our computational models, right? So the way that we calculate things with divisive normalization, you can say it's like a blend of different things that happen in convolutional neural networks. Like, I don't know, I just put up two here, like max pooling and softmax, right? This softmax also sort of limits the amount of response that you have at a certain point. And there is a sort of neighborhood type computation happening there. I think in general, the idea is that, or the idea many researchers in this field have, is that you are doing things to create a process similar to divisive normalization, but you're using completely different tools, right? Because, you know, when you're building a neural network, then you're also confronted with things like computational constraints, for example, right? Is it easily implemented in a GPU? Can you, can you make it, vectorize it, that sort of thing? All right, but yes, this type of processing, you can see specific sort of echoes of in artificial neural networks. So I'm gonna take steps to make this a bit more concrete, right? Because it now is this idea of neighborhood, which is totally vague, right? And we're going to make it more and more concrete as we go along. So the way that we would fit this into an equation is makes for a very, very simple equation. It's this division, right? So you see the fraction is the largest part of it. You are looking at an output response, right? So that's the thing all the way on the right. So the equation is flipped left, right, compared to the diagram. So y is the response that we record, right? Y1 would be the linear response of the stimulus. So Y1 is the activation to a given stimulus where we record. But this is not just this is not the only response that we measure. It's not the only constituent of the response that we measure. So y is y1 of x plus b perhaps would be this, just the upper row here. But we now also model this normalization pool, which also has its own constant there. Right? Important to realize that the normalization pool also just responds to that same stimulus. It just responds differently. Yeah. So it's a very simple equation. And so the takeaway here really is that you see neuronal responses not just as input-driven activations, but as this ratio of input-driven and contextual activations. And this also means that we never fully have access to this Y1, right? You never see it because you always see a normalized response. And this is a very important thing to realize. Yeah? It's similar to like the thing with the hit rates and the false alarm rates, right? In a signal detection theory experiment, you don't actually have access to the sensitivity. You need to, you know, take it from the model. Like you only get it after you've done some, you estimate it from the data, right? So now these first V1 single cell responses that the model was created for, how does it do that? Well, as you increase grading contrast, you would say that if this is just weights times input, you would expect that if you increase the contrast, then you would get just a linear curve, right? It's just dot product. You have X input, you get Y response. If you put in 3X input, you should get 3Y response. If you put in 100X input, you should get 100Y response. But that's not the case, right? People saw that if you increase the strength of the input, you get this saturation in the response strength. So this is because of the normalization model, you get it's not just y1 that increases, but also y2 increases, and therefore it will saturate at some point, right? So this is also necessary, right? It's important to realize this is necessary. You cannot have a neuron with a response rate higher than, I think the peak is like 200 hertz or something, but there are no neurons that fire more than 200 hertz. But if you have a linear neuron and you present very loud sounds, then it's physically impossible for a neuron to linearly respond to that, right? So it's necessary that we have this sort of saturation, in this case for contrast. Now, secondly, because the normalization pool is the neighborhood, it's slightly larger than the activation pool. And what that means is that if you place a stimulus around another stimulus, like as a surround, it will activate the normalization pool, but less so the activation pool, right? So by adding a surround, we are increasing the denominator of the fraction, right? So we are increasing y2. And what that means is that we can change this response to the center by modulating the surround, right? And if you here have this saturating response without see this, right? Saturating response without an annulus around the stimulus. So here you have the center stimulus in the middle, right? It's similar to this one. And here we're putting stimuli around it. And you see that this response curve shifts all the way to the right, where for the same stimulus at 25%, you get like, what is this? Like 4 or 5 times the response without a surround than you do with a surround, right? This is a huge modulation because of this surround. And this is because if we go back to that equation, right, the fraction, it's the bottom that's being increased by the surround, whereas the center, the top of the fraction, the numerator is the same. So you're dividing by a larger number here, right? And what's cool here is that you already saw this from experience, because this is this, right? This is that perceptual example that you already saw. It's the middle looks like less because it has a surround around it, right? So this firing rate curve that you see here, that's really what your perception corresponds to in this example. And again, this is just a simple dividing the center by a surround, right? By a context. Yeah, so I really like this fact that you can show something in terms of perception. Well, only one of you didn't have this effect. It's something of a weird brain, perhaps. But
my how did I choose this? Was just because it was the higher contrast.
you thought it must be the highest.
No, because I had to fill it in. It was the only one that fit it.
Oh, you looked at the specific pattern? No. You just did, like, you moved your eyes around or something.
No, I just felt like it was the only one that could fit because of the contrast.
Oh, yeah.
They're kind of blurry, so.
Yeah, but the others thought it was the second from the bottom. Right? They would have done the same thing, but they thought it was a different one. Okay, fair enough. In any case, what I like here is that you see something in perception and you see exactly the same in a neural measurement, right? So what that indicates is that, what your perception is just doing is a reflection of that neural measurement. Okay, so I'm going to switch topics a bit for a couple of slides and then move back. So we've now seen these very low level perceptual and neural measurements show this effect of this normalization, right? And we'll at least show these effects that we can explain with this normalization model by just saying that this is all just a simple fraction of things. And I want to turn to one sort of topic in higher level cognition that people have applied this normalization model to also. And that is attention. And usually, who of you know what attention is? Yeah. I don't know what the others were thinking, because, as you know, William James in 1890 already said, everybody knows what attention is, right? So it's as if, like, someone says this word, like attention, And it's such a colloquial term that everybody knows what it is, right? And he then put it into words like everybody knows what it is. It is, and I have to, it's like the taking possession of the mind in very clear and vivid form of one out of what seems of several simultaneously possible objects or trains of thought, right? So here you already have one out of many, right? So that you have a center and a surround, you have a activation and a surround or thing, right? Focalization, concentration of consciousness are of its essence. It implies a withdrawal from some things, a suppression, in order to deal effectively with others, right? So there's like a contrast inherent to that, yeah? It's a beautiful description. William James was an excellent writer, very beautiful description. But he's also wrong. That is, attention is such a colloquial concept that everybody may feel like they know what it means, but that doesn't really make it a scientific concept, right? And that's really hard because every field has its own description of what attention is, right? Do we really know what attention is, right? Everybody has their own idea about this, right? If you look at transformer network for natural language processing, right? You have this attention, self-attention process, right? The dot product between the, what is it? I forget, the Q and the K or something, the V and the, anyway, I forget that. But this is like this multiplicative interaction at different delays, right? Between the meaning and the order of things. It's a multiplicative interaction. It constitutes this focalization, this concentration, right? That's what you get, this process of attention. So you see why people would call it attention, right? But if you then look at a different field, it's completely different, because in cognitive psychology, people have this thing that they say is also attention. So people first, you have this singleton target, no distractor on the left, right? If I ask you to, what I'm going to ask you is to report the orientation of the line element inside the circle. Now, this is very easy, right? Because as it pops on the screen, you see which one of the is the circle, and then you say, oh, it's horizontal, right? That's a very simple task. People are generally really, really good at it, right? But then in this singleton target distractor condition, the middle one, which is the most important for this, if I now make one of those squares that used to be like just there for filler, make it very, very salient, it will pop out, which we call attentional capture, and it will make you slower and worse at the circle position, right? The circle here is exactly the same. The answer is the same. You will be slower just because the red thing just pulled your attention away. Yeah. This is also a multiplicative thing, you might say, right? It's just, you know, it's based on a different principle. It's a bottom-up type of salience thing. All of these are also just words, right? But it's a completely different thing, right? There's this multiplication somehow involved, but that's about it. And then if you go and ask marketeers or advertisers, IKEA says attention makes everything more pretty or more beautiful. I have no idea what that means. I don't think that advertisers knew. But you know, you can even use the word attention in a context like this, and people will feel like it means something. Right? So what is attention? No idea. Yeah? It's similar to consciousness, for example. Like the field of consciousness research has a main problem in that no one agrees what they're researching. Yeah, you can see why that's a problem in science. Right, so this is something that you know, we need to nail this down. Like, what do we agree upon is attention, right? And this definition of William James is already pretty, it has some hints to it, right? There's this multiplicative type thing, and it has this out of several simultaneously possible objects or trains of thought. Like there's a context there already, right? And so again, this dude David Heeger, who's really, he's a nice guy. He devised a way of thinking of attention in a context of normalization to explain different responses that people had seen in the brain. So, you know, looking at, again, at neural measurements and how they behave under conditions of attention, because people were really confused at this time. Attention could have different effects in the brain, and they had no idea, researchers had no idea why this was. It turned out that, as you can see in B here, attention could have what we call a contrast gain effect. So what that means is that if you have attention on something, on a stimulus, the response to that stimulus, so there you have the contrast again on the right? And so this is the response percentage. You see this nice sigmoid curve that we've seen already. What would happen is you pay attention to that stimulus, and the curve would shift to the left. So for a given contrast, you would get a higher response, especially at the steepest part of that curve, right? So that's a contrast gain effect. But other people in the same field, they found that no, you don't get this contrast gain effect. You just see an increase in the size of the response. So it's not a shift to the left, but it's actually a scaling up. It's the maximal response that increases. So that's a response gain effect. And people had a really hard time figuring out what the hell, right? And you can see that in a field where everybody just uses this term without actually agreeing on what it means, that can be incredibly problematic. Now, what these authors did, this is also in the review paper that you'll be reading, right? So you can dive into this a bit more deeply. The idea is that attention functions by means of a pool, like as a normalization pool, and it is both multiplied by the input and by the normalization pool, right? So there's just it increases processing in the activation pool, but also in the normalization pool. It's like an extra normalization pool, if you will, or like a multiplying normalization pool. And what you then get out is that you get a population response that's biased towards one of two options, which is what you can do with attention, right? You can focus your attention on one of two options and neural processing will increase, like you see on the top. Yeah. The nice thing about this is, we have this context in the normalization model, right? The context is important. And what they show here is that it's the size of the attention, so that is a normalization pool that you can scale, that you see is different for those B and C, that allows you to predict different effects. Yeah. So if you have, and this is, so if you have a very, very tightly focused attention, right? So at this very focused position that you see here, so here you see attention is really, really focused. Yeah? So what that means is that this normalization pool is also very small, and that means it doesn't get large enough to keep the responses very low, which means that the maximal response can increase because the attention field is so small. But if the attention field is large relative to the size of the stimulus, you actually also address a large normalization pool with your attention, and that will cause the maximal response to remain the same, but it still has this effect by shifting the curve to the left for you. Okay? And so this allowed them to explain these two different responses. They just found out that in these papers that people were using different attentional manipulations. In one case, the attention field was relatively narrow and the stimulus was very large, and in the other, the stimulus was small, but the attention field, like the way that they were directing attention, was very broad. And this allowed them to explain these two different patterns in the results.
The attention field in the diagram below corresponds to the attention gain factor.
Yeah.
And is the amount of information we can attend to?
Yeah, you could say that. Yeah, you could say.
It's not always visual, right? It's anything that
In
this experiment.
It's also tactile, for example. Like you could see this as so this is position and orientation, right? This is two gratings on the screen, something like that, like you see here. Right? This is actually analogous. They could also be like fingers, like I put a buzzer here or something, right? And I use the frequency of buzzing or something. It's completely general in that sense. Yeah, so people use vision always, but it's not, it's you hope that the principles that you find are more general than that. But it's, yeah, for many reasons, vision is.
We like V1 rule.
Yeah, well, you should tell that to Serge Dumoulin, my collaborator at the Spinoza Center. He's always about V1. Can we show it in V1? Which is fair. I mean, if you can show something in V1, then it's definitely there. Okay, so I'm going to take a step back. This was just an example of how, even a highly cognitive process can actually be explained by normalization, right? Just like this idea that you divide by the context. That's in general just the idea, right? And if you multiply some manner of processing and then that features into the division process, then you get this attention field model. Yeah. But there's also other things that people have found that people have thought you need different models for. And it turns out that this divisive normalization model can actually capture a variety of these responses. So what I'll be segueing into now is this research that we have done where we do these receptive field measurements that I've explained in the receptive field lecture, right? And then we see these different signatures of responses. And it turns out that you can actually capture these really nicely with this divisive normalization. Yeah. So one of these signatures in terms of activation is deactivations that we see, right? So this is an experiment very simple to the one that you've already seen, that you saw with these colored thingies that passing through the screen, right? That's a very standard type of experimental design. And this is more or less identical. What you see here is that the bar passing like from the bottom to from the top to the bottom in the different directions. And what you see here is that if you have a standard linear model, right, which is just shown here by just a single Gauss, you see that you get these activations that the model predicts very nicely, right? And you can actually fit the parameters of this model. You get a position, you get a size, beautiful. And this is already capturing like half of the variance, but you see that you're not that there's a signature in these data very compellingly that you're not capturing, right? And like this is work done already 10 years ago, but it turns out that if you make a differentive Gaussian model, so you propose that there is a larger receptive field that subtracts from the center receptive field, then you can actually have these negative responses, and then that allows you to explain the data much, much better. Yeah.
So you include more context?
Yeah. So in this case, you have a context, which is the surround, right? But here, it's not divisive. It's not divisive. It is a difference of Gaussian. So it's a subtraction. Right? So it's algebraically, it's a different operation. Yeah. Good point. Now, this is just to show you like one of the aspects in the data that people couldn't explain before, but could explain with this model. It turns out there's more to these time courses that we just don't get or didn't get way before. One is that you get sublinear time courses, and this is also in the practical, right? How do we make responses that sort of compress at the top, right? That don't continue linearly. And so here's an example of this paper by Kender K in 2013, where he shows like, what if you have a receptive field that's right on the edge of this this stimulus, right? It gets activated half by this stimulus, and it also gets activated half by this stimulus, right? They're both right in the middle. So what then happens when you show the full stimulus, right? You would think, like my example of the saturation, right? That you get a response to one half, you get another response to the other half, and then you take the two together, and then you get your final activation for the full stimulus, right? Easy peasy. That's a linear prediction. It turns out that even in V1, when you take the activation to part 1 and the activation to part 2, you sum them together, you would expect this signal change. You are pretty far below already. So there is some compression going on in these responses. And this effect is much, much larger as you go up the visual hierarchy. Here's an example for V3. If you add this to this, you get that, but we end up with this, right? And you can say, okay, what's the ratio between what we expect to get from the summation and the actual measurement, and that in V1 is 0.8. So this is about 80%. Think of that at the ratio between these bars. But as you go up the visual hierarchy, this gets lower and lower, and it gets like half, which means you get only half of what you expected for a linear model. And how do we model this? Well, it's a very simple model that can capture this, and what it does is just raises the linear response to some power. So you can exponentiate, if you will. So you take the, right, and as you know, if you make this n value of 2 or something, you get an explosive curve, right? It's a quadratic curve. It goes up and up and up. But if you make this lower than 1, it will become more like a square root, right? Like a log function. So it will start to compress, right? And so you can use this n. If it's smaller than 1, you have a compressive summation. And that's what this model was intended to do. So this is just one of those signal characteristics that the linear model just fails at. Right? And people needed either this difference of Gaussian or this compressive spatial summation model to explain these different types of responses, but they are mutually exclusive. So you can start out with this Gaussian model. This is just a linear model, right? You need a different model to do negative things. Well, the square root function, for example, it's never negative, right? Unless you go into imaginary blah, blah, right? It's never negative. So the CSS model cannot explain what the difference of Gaussian model wants to explain. And the difference of Gaussian model cannot explain what the CSS model wants to explain, because this one remains linear in terms of its signal increases. It just subtracts this, background, this one. Right, so here you have the center, right? Here's again the center with a surround. It's larger. And this one is just at center, but then exponentiated. Yeah. But it turns out that if you just make a divisive normalization PRF model, right, which is not the subtraction of these two, but the division of the two, and add these B and D parameters, which are just like constants, they don't vary, then you have a divisive normalization, very simple divisive normalization PRF model. Yeah. And this is so our PhD student, Marco, created this model. And of course, then we needed to show, okay, can it do what the difference of Gaussian model can do? Can it do what the CSS model can do? And can it do both, right? Because that would make it a very parsimonious model, right? Really in the vein of what normalization does in general, right? It's a very canonical, very general computational principle is the idea. And so we're looking at, again, this sort of time course where you see these bars passing throughout the experiment, right? So this is like 5 minutes or so. You see here that there's a voxel. We're recording from a single voxel. And you see that this has all these negative deflections, right? There's suppression in the time course, like the surround suppression, similar to what you saw with well, everybody but you saw in the center of with the contrasting, right? So you get this very nice suppression response, which the difference of Gaussian model can explain. See, this is the linear model, and this is the cross-validated R squared. So the difference of Gaussian model is much better than the linear model. The CSS model really cannot do anything with these negative things, but this divisive normalization model can do exactly what the difference of Gaussian model could do, right? It can capture these negative flanks. But if you go to a different brain region, you get these really weird nonlinear responses, right? They don't look nice and spiky as a linear model predicts, but they look like very plateauy, right? And that's what you get when you compress responses. They can't keep growing, but they just flex off. And so this is also what you see, right? You see that the linear model, it really wants to go down and then up again for very limited stimulation. And this is much better fit with the CSS model. There's a lot of compression here. So comparing the standard model to the CSS model, this is where the CSS model excels. But the divisive normalization model can also capture this, right? So it seems like it can do both of these different things. But these are two caricature voxels. Marco spent a lot of time looking at them. But one thing that's also very nice is you have these voxels where, so this is like a population of neurons, and it shows, and this is something that's problematic with having these two different models. This population response, this voxel response, shows both compression and suppression, right? And so it means that only part of this response you can capture with the difference of Gaussian model, and only part of the response you can capture with the CSS model. You actually need a model that can do both of these things in order to explain the responses here. And this is exactly what you see in a voxel like this. So the linear model has around half of explained variance. Both the difference of Gaussian model and the CSS model improve on this significantly, but you can get much further if you have the divisive normalization model, right? So what this does is it captures the improvement for the CSS model, and it captures also the improvement for the difference of Gaussian model. It can combine these two things. And here's another example of how that would work, but with more compression. Yeah. So how does this work, right? So what's nice is if you have a model and you have a reason for doing this, right? This sort of computational principle of normalization. What's cool is if you can then start to see, okay, but why does it do this? And for that, we need to try to understand what the parameters of this model are doing. And there are a couple of important ones. So I've put the model to the right here, right? So I can point you to the different parts of the model. Just this minus b over d is just there to make sure that if there's no stimulus, the response is 0, right? If the response is, if there's no stimulus, this is 0, this is 0, and you would otherwise end up with a prediction of b over d. You need to predict 0 because there's no stimulus, and so you have to subtract b over d. So that final part is not interesting. Yeah. It turns out that you have these two parameters in the model, b and d, that do different things, but they allow the model to start behaving like a difference of Gaussian or like a compressive model. So if you take b to be 0, then, well, there's nothing to be suppressed, right? And you get a linear model. Yeah? But if you then increase b, that gives the model something to suppress, which means that it can start to go below its baseline. And that's when you get these negative flanks. Yeah? Similarly, if you make d really, really large, you're always dividing by something really, really large, which means that the normalization pool really doesn't do that much other than just let through a linear response. Whereas if you make this very small, it means that you get a large effect of this division in there, and that makes for a beautiful compression. So the smaller this d is, the more compressive the response. Yeah, so you can simulate based on these parameters, right? And then you can formulate a prediction, right? Okay, this activation and normalization constants, they should modulate suppression and compression, right? So we can try to see, like, if this divisive normalization model captures this difference of Gaussian responses, then it should do something with a B to be able to do this, right? And if we see that it has very compressive, that it's fitting very compressive things, then that should have a reflection in the D parameter. And so you can do that. You can then start looking at the data. I'm pressing this button, but it's not doing anything. Oh, now it is. Strange. So we simulated this now, and then we do this experiment. Well, you've already seen the experiment, but that was just for the time courses. It turns out that as you go to the higher levels of the visual cortex, the B constant decreases. And similarly, the D decreases, and what that means is that you get less suppression going from V1 to higher levels of visual cortex, and you get more compression as you go from low levels to high levels. And this is exactly what we already knew. We knew that the difference of Gaussian model was best for V1 and V2, more or less, and that the CSS model was better for all of the high-level visual regions. And so this means that this difference of Gaussian and CSS division in terms of the visual system is actually shown also in these parameters of this model that unifies them. Yeah? This is also shown if you plot this activation constant as a function of the surround strength. So how strongly suppressive is this thing? Well, it turns out that that's highly correlated for V1 and V2. Similarly, there's a strong correlation between this exponent, so that is how compressive the response is, and this D parameter. Same thing, right? So it really seems like this model can capture, this DN model can capture these previous models, yeah?
RP and D just abstract.
Yes, very good question. Like, because we might be at the computational level, right? So we're describing this also all in terms of like a computational principle, maybe a bit like an algorithm, but it's not an implementation level thing, right? Like what would it mean in terms of neurons it's more or less what you're asking, right? So my answer has two parts. And the first part is we're not at that level, right? We're trying to still remain at this more computational abstract level, right? With the Marian levels. The other is we have thoughts about this, and I'll go into that in a bit, yeah, at the end of this slide, I think. So Yeah, you also see that, just a quick explanation of this middle graph, right? If you see that the differential Gaussian model is much better than the linear model, which happens in V1, that also means that B is much higher, just like I explained in the, like would be the case, right? And the same type of correlation holds for the D parameter and how well the CSS model improves on the linear model. Yeah? So it really seems like these different signatures that used to be very diverse, right? That used to be these reflections in the data. We used to need different models for these different things, but there's really no reason to use different models if you can have a single computational principle that brings them together. And that's really the idea here, and I think a beautiful example. So to get back to your question, this is an excellent question, because you do want to go from level to level, right? You do want to be able to say, we know from a computational perspective that this and this and this should be the case. And what this predicts is that at the implementational level, this and this and this should be the case, right? You can try to, use the knowledge that you've gotten at one level for going to another. And so if we look at this this sort of pictorial equation on the right top, I can try to explain what we think B and D might mean. I was talking about B before as something that you have that gives you something to suppress. Yeah, that's what B would be. It would be something that needs to be high for the normalization pool to be able to bring it down. Yeah? And so what would that be? Well, it would be the firing rate of the activation pool without a stimulus, right? So if at rest, your neurons are firing really hard, that means that if the normalization pool starts implementing its division, this firing rate should be going down, right? And that's suppression. So we think that B is the baseline firing rate, if you will, of the neurons in the activation pool. Yeah. And similarly, the same holds for D. It's also constant. So it means that that would be the firing rate of the normalization pool at rest. Yeah, so the larger the firing rate of the normalization pool, the stronger or the less strong the compression. Yeah.
So in terms just of like trying to approximate the signal, and you said B allows us to go lower, so more negative responsive measurements, and D allow us to compress our signals, like more like
And so it's important to realize that B, so in the way that you said it, B needs to be higher for there to be suppression, right? But D is the opposite. D needs to be smaller for there to be compression. But that's just the way the division works.
Yeah, so if B is high, then we're going to be able to capture lower
dips.
Yeah,
exactly. Right, so this is we were really happy with this because so Marco is now doing we're now trying to publish a paper where we're relating this also to receptor densities that you can measure using PET imaging. So what this means at an implementational level, I was saying just now, baseline firing rates, these would be under the control of different receptors, right? Different neuromodulators. So we have some hypotheses. It's going too far, but this is really where we're trying to go. Like again, your question, trying to bridge these different levels. Yeah. Okay, so one other thing is you can talk about this normalization pool, but it has a free parameter also, and that's its size. Right? It can be smaller or larger relative to the activation pool. I didn't talk about that up until now because I wanted to focus on the B and the D parameter, but it turns out that can explain something called spatial oversaturation. So if you increase the size of a stimulus, normally you would drive a neuron, for example, more and more and more, and it would saturate, right? Like we just talked about, it would saturate. Turns out that in many neurons, the response actually goes down after that. And that is thought to be due to the fact that you are you cannot do much. So this is centered on the activation pool. You cannot drive the activation pool more than with a stimulus of 0.3, for example, or what is it, around 1. If you then increase the size of the stimulus, the only thing that you're doing is you're stimulating the normalization pool more. Yeah? That will increase the denominator of your fraction, making everything go down again. Yeah. And so there's two phases to this, right? So this is that standard compression, right? It bottoms out at the top, or tops out. Yeah, tops out at the top, right? Yeah, you get the point. So that's the first, right? That's the first nonlinearity, and the second is here after the peak, where if you keep changing or keep increasing the size of the stimulus, you'll start driving that normalization pool and bringing it down. And this is really cool because this is an intuition that you have when you think about this, perhaps already, right? The way that I just explained it, but it's actually very, very clear in the model that these two different nonlinearities, they can be brought about by these two different parameters in the model. So the first is this D that I already showed you, right? That causes compression when it goes down. But we also have this ratio of stimulus sizes. And as that ratio becomes larger, you get more of this oversaturation for larger stimuli. So you can actually create this spatial oversaturation that I just showed you as an example from single cell physiology by a combination of the D and this size ratio parameters, right? So if that is the ratio of the middle, the activation pool, to the outside, the normalization pool. Yeah. So it's quite nice that you have these two nonlinearities in these responses that you can get from animal physiology, and then you have two parameters in your model that you can get from both responses, and then check that out. Right, so it's important that we created this phi thing. It's just the size of the normalization pool over the size of the activation pool. Right? And then, of course, you can go into the brain and you can show that this phi, this parameter, it goes down in a way that's very similar to D as you go up the visual hierarchy, right? So the different levels of the visual system, they have different ratios in terms of sizes. And if you then translate that into what the size response curve looks like for each of these different brain regions, it's actually very, very similar to what neurons show. So what we think this model also allows us to do is translate between different modalities, right? We can actually take a lot of cues from animal physiology and then start using them to interpret both responses. Yeah, so that spatial oversaturation is really driven by how large that normalization pool is relative to the size of the activation pool. The larger it is in lower levels of visual cortex, the stronger this oversaturation here on the right of that middle curve. Yeah. You also see that the compression, which is how strongly this goes up with the minimal stimulus size, is largest in higher level visual cortex, which means a smaller size ratio. So the normalization pool is relatively small. And we also have this D that goes down accordingly. And this is not something that either this difference of Gaussian model or the divisive normalization or the CSS model can capture, right? So we had these earlier models, they could do one trick really well. This one can do more tricks. Yeah.
The sigma is not present in the form of
the sigmoid?
No, like the size of the stimulus is not in the form of the device.
Oh, no. You have to do some calculations, like a bit of math to, so you have to like assume that you're stimulating the receptive field with a stimulus at its center and then increase the size. So it's a bit of a, yeah. No, you're right. It doesn't fall from this like pictorial equation immediately, but you can derive it from it. Yeah. Let's see. Well, you can include it in your experiment. So you can do an experiment where you're actually manipulating stimulus size in a specific way. And then you would be able to actually measure this curve. But in the way that we're doing it here, we're taking the fits from the PRF experiment and simulating what would happen in an experiment like that. Yeah. Good points. So that's all very detailed and very like onto like bold responses in the specific receptive field model. What I hope I'm showing you, apart from all of the details, is really this idea where you can take this general computational principle, like a canonical computation, and then apply it to a given model situation. And in this case, that proved to be very, very fruitful. So to recap, right, this concept of the canonical computation. So first, people try to think of these things as these sort of electrical engineering diagrams, like circuits, right? And it turns out that the circuit doesn't constrain function that much at all, right? You can have different computations running in the same neural circuit. So that's really not what we should be looking at. That's a much too implementation-based, if you will, approach. But we need to focus on computations instead of circuits. And then when we start searching for these canonical computations, what we want to find is this sort of principle, like a computational module, if you will, that the brain reapplies in different settings, and thereby is very frugal with how it computes, right? It doesn't need to reinvent the wheel. You just try to use the same computation, but it has a slightly different role in many different contexts, right? So it's just a very basic machinery. And in this case, that is the division concept, right? So that's how we think about what divisive normalization. I always forget how I should call this, divisive or divisive. People argue about this. I don't, yeah, who cares? Yeah, right? Yeah. Yeah, that's difficult. Yeah, we can argue about that later. Yeah, so the idea is really that whenever your brain needs to take into account context, like you saw in that perceptual illusion, divisive normalization provides a way of explaining what the brain is doing in that situation. And then the idea is that, you know, you always try to think of this might be maximally stimulating some activation pool, a stimulus, for example. There are also other neurons that are perhaps a little less stimulated by it, but they're also stimulated by it. And this gives you this normalization pool, a contextual response by which you divide, right? So you're not looking at this activation pool sec. It's always this ratio between the two. So historically, this came from neurophysiology, but now you can, you know, people apply this also to things like this cognitive psychology thing, the attentional capture. You can also do modeling of that type of principle with this. Like I said, value-based decision making. I showed you this detailed example of how the population receptive field model can be extended with this principle. And that really allows us to explain very different responses throughout the visual system in humans. Yeah, and then what I think this nicely illustrates is that you have this very diverse set of things that your data are showing you, right? And then if you find the right way of looking at it using a computational model, it starts to sort of fall apart, and you can start to interpret what your data are doing through the lens of these parameters. I think what I hope that you're taking from this lecture, apart from all of the details that I wish you remember, is just this idea of how using a simple computational model can sometimes really make a problem just fall apart, where you really start to be able to cut it up into very manageable different pieces. So that's for today. Third practical, where we're going to the third practical occasion where we can run through the second practical file is on Friday, right? So you can take what I've shown you in this lecture and what you're reading in the literature, the final paper, that will definitely help you with doing that practical, going through that practical. If you need any help, Shufan, Ron, and I will be there on Friday. Yeah.
What I got from the lecture was that we have a stimulus X and we have a response Y. And if you add context, the response is gonna be lower. But I don't know, it's weird because
It's more.
can give you more information.
Yeah, but is more information. So yeah, if you're at the center of a large stimulus, right? If you're a small receptive field and you're reporting something about the center of a large stimulus, should the brain care so much about what you're reporting? Well, not really, because there's a lot of stuff around that carries more or less the same information, right? Because it's one big object, and you don't really add that much as your small receptive field in the center. So it makes sense for the brain to actually decrease responses to things that are less relevant, right? So you can think of this normalization principle really as a sort of automaton, like a little piece of machinery that allows the brain to focus on things that are important for subsequent function, instead of being drowned by responses to things that are irrelevant, right? So you can see this as a sort of relevance detector. Yeah, I hope that makes sense. Right? If something is very uniform, right, you want to see that thing that pops out. Right? And the way to do that is for all of these similar things to be normalized away, and that single thing that is different, for it to that can rise above this normalization, right? So it's you can think of this normalization also as a contrast enhancing mechanism. It's a very automated thing that, like in a convolutional neural network, the brain just applies at every different level again and again to sort of fine-tune function, to make it more specialized. I mean, it's always special, but
Can you say it's like a attention mechanism?
well, so yeah, it's not strange that you can use the same type of mechanism to explain what attention is doing in the brain, right? It's a sort of automatic attention, if you will. Yeah. Yeah, I didn't mean to invent a new concept attached to the word attention, because that's just horrible. But yeah.
And attention is the same as focus, or let's not talk about that now.
Yeah, no. You can think of it as focus, I guess. Yeah.